Good afternoon, dear audience. And this is the Tah Poe Seminar Series 51, number 4. And before introduce our speaker today, I have some message to the audience. And for the audience online, you can leave your message on the chatting place or Facebook or YouTube channel. It's okay. And we will ask your questions to speaker by the end of this talk. And for the audience on site, especially for students, and you are especially encouraged for asking questions by yourself, and you have to practice this. Okay, so if no problem, and our speaker today is Professor Sikarin Yoo-Kong, and okay, let me call you Professor. It's okay. Yes, and his topic is about entropies, fish.
Okay, is that all right? Okay, so thank you very much, for your kind introduction. So, well, today's topic is about entropies, feature information, and their generalization. Actually, the first plan that I would like to present is actually just only feature information, and it's generalization. But actually, our motivation actually coming from the variety of the entropies that we have so far in the literature. That is the reason why I also include the entropy part into the talk as well. And well, for the part of feature information and the way that we generalize it is joint work with my student, Watershed with Gail, which is actually stand there. Okay. All right. So this is the plan. Well, I'm going to talk a lot on different type of entropies, starting from the standard one, like a thermodynamics one, and then we move to the statistical mechanic ones, and then we talk about the entropy from the information perspective as well. And then we're going to talk about Kullback-Leibler divergence, and then we go for Lenji and Solis, and Sharma-Mitchell entropy, and then 2 parameters of the Kullback one. And then after that, I'm going to introduce you guys about feature information, and then we're going to present you how the way that we generalize this feature information by employing the connection with the least action principle here. And then we get 1 parameter feature information, and then we also extend the idea to obtain 2 parameter feature information as well. And at the end, I'm going to give you a conclusion. All right? Okay? So, start from this very basic thing, thermodynamics entropy here. So, suppose you have a cup of hot coffee here, and like you leave it in this room. After 10 minutes or maybe hours, right, your cup of coffee will will cool down, right, because the heat transfers out to environment, right, like in this picture, and then eventually, your cup of coffee will have the same temperature with the environment, I would say, right, and the interesting question is that, so will this cup of coffee again hot on its own? Is it possible? Well, the answer is a big no, right? Because the heat cannot transfer by themselves, right, from the environment, which actually have the same temperature with the cup of coffee here into the cup of coffee and make it hot again. This is the impossible process, right here. And and then this is the reason why it cannot be happen, because this is against the second law of thermodynamics, right? And well, actually there is different types of the statements of the second law of thermodynamics, right? You can have like the closest statement actually related to the, I don't know, well, heat engine, that kind of thing, that you cannot build up the perfect heat engine, something like that, right? And well, you have another different statement as well. And then, but well, this is the one that actually related to the quantity that we call entropy, right? Which is statement of this one is that the thermodynamic process will occur naturally in the direction in which entropy of the universe increased, right? And well, we get this kind of relation here, and then well, you get the equal sign if the process is reversible, something like that, right here. Well, this is what we learn, well, we know so far, right? And so, next thing is, in statistical perspective, suppose now I have two boxes, right? The first one is the red one, which actually represents the very hot box of gas, right? And the blue one is, well, is the very cold box of gas, right here. And then I attach these two boxes together. The heat will flow, naturally will flow from this hot body to the cold body, right? Because this is allowed by the second law of thermodynamics, right? But well, this process is kind of the macroscopic view, right? Well, but actually, if you look inside into the box, there is kind of a molecule of the gas here, right? We should actually suppose that, well, there is some, well, a configuration of the molecule of the gas, right? At this beginning of the time, and some later time, this might change that configuration, something like that. And well, the motion of every atom, this in this box can be captured as a trajectory on the phase space. If you could, well, if you have the Hamiltonian this way, and then you can compute you can have the Hamilton equation here, and if you can solve this Hamilton equation, you're going to have this trajectory on this phase space here, right? That is very simple way. Well, but well, in practice it might not that simple, okay? But support, okay? And well, there is some theorem which it actually states that suppose this is a region that we are interested in, which it, you have to be, well, imagine that actually this is the hyper volume, right? That contain, well, the dot here represent one of the possible state, right, of the system. And then this whole region will evolve to be a new one here, right? According to this Liouville theorem here, this one dot will be mapped from this one to this one, right? This is one-to-one mapping here. And then it means that the number of dots in this hypervolume will be preserved somehow, right? That is the statement of the Liouville theorem. And then now I can define this quantity as a density function in the hypervolume, right? And then if I integrate the whole region that I am interested in, which is actually labeled by this is gamma, right? Yeah, that I call this ensemble, right? So in this sense, the ensemble is the collection of all possible states that your system can access in this phase space, right? Something like that. And then with this definition, well, the Boltzmann gives the simple relation between entropy and a number of all possible microstates. Well, this is all the dot is all possible microstate, right? That your system can access somehow. And then you get this a new type of entropy that we know that actually Boltzmann entropy here, right? And then this can be the Boltzmann constant. Well, And well, I have a note here. Actually, the Boltzmann gave the first this statistical entropy in his kinetic theory of gas, and later Planck reformulated it into this current form, I would say. But well, there is another fact that actually at the moment that actually Boltzmann tried to think about this formulate of this kinetic theory of gas and entropy in this way. At that point, the people understand that actually the way that heat flow from the hot body to the cold body, there is nothing else fundamental more than that. The nature is that thing, right? But Boltzmann believed that there must be something more fundamental than that. And then he started to investigate that. And then he come up with this idea that actually the macroscopic actually emerged, the behavior of the microscopic actually emerged from the macroscopic emerged from the microscopic scale, right? That is the thing, okay? So suppose now we have this picture. Suppose I have a box of gas here that I confine this group of atoms in this particular corner. And at some later time, if you leave them, and then it's going to spread out to the box, right? And then it eventually going to be end up spread out everywhere in the box, right? This is like most probable configuration that actually your system going to evolve to be later on, right? This is is not likely to be in this case, right? In this situation. The thing is that according to the law of large number, this route is the most probable. But if you put the gas like two atoms of gas in this box, this situation might actually happen, right? Because you have only two atoms of gas, right? But if you have a bunch of them, like the n is very large, then the law of large number will tell you that actually this is the most probable configuration, something like that. Okay, now, so the second law, now we restate the second law in a new statement like this. The total entropy of any isolated thermodynamic system tend to increase over time, right? And approaching to its maximum value, right? That is a new statement of the second law of thermodynamics. To make it a little bit more clear, that actually the way that we explain the behavior of the thermodynamics process from the statistical mechanics point of view and the thermodynamics point of view, they're actually consistent. I'm going to give you this example. I really like it. So suppose I have, again, two boxes I call A and B, right? And then actually there is, I partition this box into four rooms here, but you cannot see it anyway. Well, in the box A, you have 3 red balls here, which is actually, you can think that 3 red balls is the energy bunch, right? And then in the box B, there is only 1 energy bunch, right? And then, if you compute all the configuration that actually you can put this red ball in this four room in the box B, there is 4 different way, right? Or 4 different configuration. But for the box A, there is 20 way that you could put all this energy band right here. And then if you compute the entropy of the whole system, what I mean is that this the whole system is just A and B, right? Then the entropy of the A and B is the additive, the add up of the entropy of the A together with the entropy of the B, right? And then you get this quantity here, right? Next, actually for this example, with in the box A here, it contains more energy bonds. It means that this, you can think that actually box A is the hot body, right? And then the box B is the cold body, something like that, right? And then now I again attach the two boxes together and then allow this for energy bonds to move around this box A and B. And then I compute all possible configuration. And then we find that actually the way that actually the two ball in the A and the two ball in the B give us modes, the way that actually we can put the ball right here. And then it means that if your initial state is in this picture, and your final state would be this one, because this is the most probable in terms of, well, this is highest entropy that we could have, right? Comparing with two other possible configuration. Then it means that, so whether you going to explain the behavior in terms of statistical mechanics or thermodynamics, it's going to give you a consistent explanation, because this means that actually the heat will flow from the hot body to the cold body and end up at the thermal equilibrium here. That is the thing, right? Yeah. Okay. But again, well, this is the most probable, and then the number that I put here is not that kind of huge enough, because, well, it's only 4 different balls, right? Okay. Okay. Next, so suppose now in Boltzmann point of view, suppose this is all possible configuration of the gas in the box at one moment in time, that I would call this is the ensemble right here. And if this all possible ensemble has the same chance to be happen, that is, well, we call the uniform distribution, right? What we need to do is only to count how many possible of configuration in this ensemble, and then we can compute the entropy, right? That what we're going to do in the Boltzmann entropy, right? But if each of the configuration there is a probability attached with it, it's like there is some bias, right? Like this one might be most probable to be happen comparing to other, right? Something like that. Then we cannot use any more Boltzmann entropy. We need a new formula which actually gives entropy here. All right, here. And well, if you look at this, you can think this actually Gibbs entropy is nothing but the linear average, right, of this quantity minus log, natural log of the p here, right here. Anyway, so again, if we say that actually, if all of them, well, actually in the uniform distribution, it means that your pk is nothing but 1 over this omega, and then you put back in the Gibbs entropy, and then you will get the Boltzmann entropy back. Then in this sense, so the Boltzmann entropy is the upper bound of the Gibbs entropy in this way. So it means that, so if you know nothing at all about your system apart from how many number of configuration in your ensemble, you're going to use Boltzmann entropy, right, to compute things. But if you know a little bit more about your system apart of how many number of configuration you could have, and also the probability associated with it, you can use the Gibbs one, right? That is the thing. Well, and then, well, this Gibbs and Boltzmann entropy is additive, which is actually I already used it already in the way that I explained this, but well, it's additive anyway in this step. What I mean by additive is that if we have two separate systems, which actually there is no correlation here, right? And then once you need to compute the total entropy of this A and B, but it's nothing else but actually you add up separate entropy of each of the system together and you get the total entropy, right? Well, no correlation, right? Yeah, I would say. Okay, next, so is going to be information entropy. Now I'm going to, well, we're going to play a game here. Suppose we have Alice and Bob, which actually are in, well, in different places, right? So, and then at Alice's place, there is a machine, what I call random machine, which is going to produce one of the English alphabet randomly, but randomly in the uniform distribution, right? Suppose that this machine produces alphabet B here, and then Alice and Bob need to communicate which alphabet actually this machine produce, right? So the question is how many questions Bob need to ask Alice. That is the thing. But the question must be in the type of yes/no question, right? That is a constraint for this game. And well, you can just like question one, is it from the N onward? If it's no, then you consider just from A to M, right? Well, actually, you can naively, well, Bob can be very naively ask Alice like, is it A? Is it B? Is it C? This kind of question, but this is not a clever way in order to communicate. Not, well, you know what I mean, right? Not is the clever way. This is much more better way in order to communicate. So the second question, is it G onward? If it's not, then we reduce another half, right? The third question, is it C onward? If it's not, then you get only A and B. And the last question, is it B? If yes, yeah, it's yes. If it's no, and then you get B anyway. Then it means that the minimum of the question is 4, right? In this game, in order that actually Bob will know actually this machine produce B alphabet from the machine here. The maximum number is 5 if the machine produce E here. You can play by your own actually. Try to think about why 5 here, right? Anyway. And we find out that actually due to the number of question is the space of the message. Space of the message is nothing but is the total number of the alphabet here, which is actually 26, right? English alphabet. And then you take logarithm function with base 2, right? And then you get, well, you get that actually number of question about, well, 4.7. This is, so this question is on the average, it's 4.7 for one alphabet, right? Because what? Why 4.7? Because minimum is 4, maximum is 5, something like that, right? On average, you get 4.7 here. And then this means that if Alice needs to communicate with Bob with 6 alphabet, then it means that your number of questions must be 6 times 4.7. That kind of thing, right? Now, I'm going to give you another type of entropy that called Hartley entropy, which is actually log of the 2 of the number of questions, and which is actually nothing but the log of the space of message, right? But if we choose to work with the log base 2, then the Hartley entropy is nothing but the number of questions here, right? But actually, well, the base of the log log function is, well, it's not that kind of fixed, right? You can choose working with a log base 10 or natural log. It's kind of, well, different currency, right? You can transform like Thai baht to the US dollar, something like that. It's just different scale. But you're going to get the same physics anyway. So then, now we have this Hartley entropy, which is actually log of the space of mass state. And if you look at this carefully, we should actually look very similar to the Boltzmann entropy. Because the Boltzmann entropy is the log of the total number of ensemble, right? Well, it look very similar here. The next one, well, in the same analogy, right? In the case that actually, if your machine in this situation, if your machine produce the alphabet not that kind of in the uniform distribution, there is a bias. Then you cannot use this Hartley entropy, but you need to use this Shannon entropy here. We should actually look very close to the Gibbs one, right? Apart from, well, constant, right? Yeah. And again, we know that actually the Hartley entropy is the upper bound of the Shannon entropy, which is actually the same that we do have in the relation between Boltzmann and the Gibbs entropy. And well, we look, well, let me give you an example. Then we can see what is the meaning of this Shannon entropy here. By playing a game again, tossing the coin, right? Which is actually, this is an unbiased coin. There is the same chance that actually going to, when you toss the coin, it's going to be to land in head and tail with the same probability, right? And then when you compute the Shannon entropy, you get one, bit here. We should actually, in this situation, in this point, we should actually, this is the maximum one in this particular example, right? The question is that, what does it mean by this one here, right? What does it mean here? It means that, so this is totally random. You cannot guess your outcome when you're tossing the coin, right? We're totally random. And well, if you look at this graph, here, 0.5 means 1/2 here, right? This is the maximum one. But if the coin is maximally biased, like pH here is 1, it means that every single time that you're tossing the coin, it's going to land in the head, always. Then the entropy is 0, right? So then you learn nothing from that experiment. There is nothing surprise you, because you know beforehand actually that actually it's going to land with the head every single time that you toss the coin, right? I put the word no supply, right? No supply. But this unbiased coin, there is fully with the supplies of your outcome when you're tossing the coin, because you cannot guess which head or tail your coin will land, right? Right, something like that. And well, Shannon introduced a quantity that called supply slope. That I put the I here, the minus log P here, and actually Shannon entropy is just a linear average of this supply slope here. We should actually look more like the same with the Gibbs one anyway. And this is the property of the supply slope. We should actually, the first one must be monotonic, decreasing in P, and must be positive, and well, I1 must be 0 because, well, the event that always happen do not communicate information like in situation actually if your pH is 1, right, you learn nothing actually from your experiment. There is no supply, right? which is actually in this situation. And again, is this supply zone is additive if these two events, they are independent. That is the thing, okay? And well, this is another note, but I could not find a reference, but well, I got it from the internet, actually. Well, then, when there is a point, there's some point, well, actually, Shannon and Neumann met and then discussed about their work, and then Shannon mentioned about a formulation that he tried to build up, and then, well, actually, the quantity that he correlated entropy, and then he asked Neumann what he should call it, and then Neumann replied that you should call it entropy for two reasons. First, because it is what the formula in statistical mechanics, well, which actually makes sense, right? And the second one, more important, as nobody knows what entropy is. Whenever you use the term, you will always be in an advantage. But nowadays, I still don't know that actually we fully understand what is the entropy is. Do we? What do you think? But I'm quite sure that actually entropy is a very, very important quantity nowadays in the modern physics. Because as you see, well, in the black hole, information paradox, in string theory, ADS, CFT, well, they use this kind of, well, entropy play a very important role, right? Okay, next, Kullback-Leibler divergence. Here is these two guys. Suppose that, well, you need to compare somehow two different pop distribution. If you say that actually you fix the P and you choose another pop distribution that you call Q, and you see how different between these two. You can use this formula to compute that kind of difference, okay? And then, well, it's called, it's a statistical distance. Well, that is a thing actually, but the thing is that is not a metric anyway for this one. However, in the information geometry context, this somehow generalized square distance in the statistical manifold. But for this talk, we are not going to get into that depth of the information geometry. Then we are not. Well, I'm not going to talk much on it, but I'm going to explain a little bit about this statistical manifold when we get into the feature information topic anyway, a little bit, in order to give you a flavor of what it looks like, right? Anyway, so the meaning of this divergence is the expect excess supplies from using Q as a model when the actual distribution is P, right? That is the meaning of this divergence, okay? And so if this P and Q are parameterized by some parameter here, I call theta here, which is actually, in this theta is actually not a single variable, it's a set of a parameter in it, right? And well, if you look at this P theta and Q theta naught, which is theta naught is fixed, and you expand your P with respect to theta naught, right? Here, and then Pj is the first derivative, and this delta theta j here. And then you expand your divergence, and then you ignore the first term is 0, right? The first term of the expansion is 0 because P is equal to the Q, right? There is no difference, right? Then you get this second term here, jk here, and this is the Hessian metric here. and it well, actually this Hatchian metric is nothing but, well, actually known as a Fitzgerald metric anyway. Okay, this is maybe look, working with a discrete variable. Let's look at the continuous variable here. Suppose that we have a mu here. We should actually measure on this set x, and then we introduce this small p and small q in this way, and we consider the variation of the p in this way by the delta q defined in this way, and then again you put all this into this equation, and then you start to expanding, okay, and then you keep only the first order of the delta q and the second order, because the delta q is very small, right? We keep only the first and the second one, all right? And then it turned out to be that actually this particular term, here, the first term here, the delta q here, you can replace this with this one, right? And then you get the integration of this q here, which is actually, this is 1, right? According to probability condition, and then you get 0 there. And then for the second term, you have this quantity, which is actually, if you look at this carefully, it's nothing but this is the expectation value, right, of this quantity. The E here represents the expectation value of these two things together. And then now, I end up with this quantity again, and with the explicit form of the GIK here. Yeah, well, it should be J, sorry, it should be J here, right here. Okay, which is actually, again, this is a Fitzgerald metric. Okay, which is I'm going to mention again when we get into the feature information topic. Okay. All right. So next, Renyi entropy. So the motivation, I believe, if I understand correctly, the motivation of the Renyi is that, so because the Shannon entropy is a linear sum, linear average, right? So Renyi just put the question that is it possible to looking for more general or average apart from linear one, right? And then he did try to formulate that, and then he ended up with this formula here that actually contain a parameter that called alpha here, okay? And then if you take alpha to be 1, you get Shannon entropy back, right? And then we can consider this is the one parameter generalized of the Shannon entropy, right? And then there is the application in the quantum mechanics because you can use this Renyi entropy as an entanglement measure. But I'm not going to talk on that topic. Well, you can ask Ninat at the back well, about entanglement measure. Well, it's a big topic anyway, entanglement measure, right? Yeah. Anyway, now we have a new entropy which contains a parameter in it, right? Next, now if you rewrite Renyi entropy in this way, we should define this is as the alpha norm. Okay, this is the alpha norm. We should measure the distance between the origin to any particular point on the simplex space. This is one of the suppose if you have 3 different p, right? This is the simplex space, and then this is a point. That is something. Okay. That is the one way that we could try to picture. I would say picturize the Renyi entropy in this way. Anyway, so and another point, this Renyi entropy is additive if you have 2 independent pop, right? You can, well, I didn't give you a proof, but you can do, well, it's not difficult to see that. Okay, Next one is the solid entropy, which is actually coming from another perspective, actually from the statistical mechanic point of view. But the Lenji actually he tried to formulate from the information point of view, right? But for the solid one, he tried to generalize the Gibbs-Bowman entropy, I think. And then there is a long history. The reason why he tried to do this, then, well, you can look on the internet. Well, there is, I think up to now, there is still a debate that actually this one, is it like, the way that he did is like, there is a group of people who believe that actually the way that he did is nothing but like a curve fitting. Because there is some phenomena that we don't understand, right? But by adjusting this parameter, right, you can fit into that curve, something like that. But there is another group of people that actually, this is a wonderful generalized entropy. Well, I don't know. You can study by yourself and then you can decide which group that you would like to be, right? Okay, anyway, if you take Q, approach to 1, you're going to get Gibbs entropy back. But this limit coincides with the Lenji entropy anyway, here. And again, but the important point is that this entropy is not additive here, right? It's not additive. Even if this A and B, they are independent, when you put into the solid entropy, you will get this kind of relation here. And it's also not difficult to see the relation between Lenji and the solids, because you can turn this summation into this way, and then you can end up with this relation between solids and Lenji here. Okay. Well, this is just a remark, I would say. Okay. But the interesting point is that this solid entropy is something to do that we call Q deformation, which is actually, I believe, this kind of one of the hot topic in math, I believe, like Q calculus or Q, well, that kind of thing. If you look at this formula carefully, and if you use this kind of Q deformation of logarithm function here, you can turn this whole formula into this very simple one. But well, this log label with the index Q here, it means the Q deformation here. And then this lawless entropy is nothing else but the linear average of this Q deformation of a log here, right? This is the reason why it is called Q deformation. But well, it's a note here. There is Q deformation of the exponential function as well, yeah, which is, I'm going to use it later, again in the context of Fisher information. Okay. Okay, so next is Chama-Mitchell entropy, which is actually nothing else but two-parameter entropy. Well, the slowest one is just one parameter, right? But this one is two parameter here. And well, if you look at, well, as I put here, for the solids is you say that actually this is the Q deformation of the log, right? But for the Chama-Mitchell entropy, which is given by this formula, which is actually, if you look at this carefully, it's nothing but this is the, well, it's twofold actually. It's the Q deformation of the log, and it's the Q deformation of the expectation value again, right? That is the reason, well, kind of Q expectation value of the R deformation of the surprisal here. Okay, that is the reason why we have two parameters in it. But well, and again, it is not additive in this sense. Okay. So, well, again, if you take the limit R approach to 1 and Q approach to 1, you will get the standard Shannon entropy back, or the Gibbs entropy back anyway. So, next topic is the two-parameter Kullback-Leibler divergence. So, I introduce here the effective entropy, probability here, P to the Q, sum of the Pi to the Q equal to 1. Well, which actually look very weird, but well, they call the effective probability. And then you can construct the Q expectation value of the surprise law in this way, right here. And then they go, well, from this paper, they introduce the called the fractional entropy, which is put in this way. And then they combine these two together, and they get two-parameter Gibbs-Bowman entropy, right here. With this formula, you can construct Kullback-Leibler divergence from this formula here in this way, right here. And then again, if you take the limit of the Q and Q parameter approaching to 1, you will get back the standard divergence back, okay? In the continuous case, well, we going to put in this way, but well, in the continuous case, the parameter I'm going to put as a Q palm and a Q double palm because I have small q already here, okay? But you have to understand that actually a Q palm and a Q double palm are parameters in this situation. And so again, if we consider a small variation of the Q, and you put back in here, and then you expand, and then you get, well, actually, you collect the first term, you will get this quantity, which is actually, this is, I would call the two-parameter generalization of the feature information here, right? Well, I will come back to this formula again when I get to the feature information topic anyway. Okay, halfway summary, I would say. So, we have this, oh, sorry, there's no dx here, sorry. This is a typo here. We have this like a Shannon entropy, right? You can, well, actually this one you can call Gibbs-Bowman Shannon entropy altogether in just one formula here. And then you have like generalization, you have linear entropy, you have solid entropy, you have two-parameter entropy here. And then all of them with the appropriate limit, you can get this back, right? This is, well, this is our motivation here. That actually from this standard entropy, you can somehow generalize, you can extend the idea to get more general version of entropy. This is the reason why we try to do the same thing with the feature information. Okay? Okay, now come to the feature information. So far, so suppose this is your system at time t, and then at some t1 later, your system may be evolved into different, well, configuration which associated with its probability, right? As I mentioned, well, the entropy can be used to predict the probabilistic behavior of the system. This is the global view, right? The entropy gives you just, well, you just predict that the whole system will behave in what way, right? But what we need to understand now is the internal structure of the system. That is the role of the feature information here. And then like how system composed and that kind of thing, how system mess off, right? Right, then we need to, well, somehow estimate the parameter that actually define the system. and then this is the role that feature information come in order to probe into the internal structure of the system. It means that with these two pieces of information, I mean entropy and the feature information, you will get a complete description of your system in the global view, right? Which is actually how your system behave, right? And feature will give you the internal view, right, inside your system, something like that. Okay, and then now I define this feature information, which is actually given by this one here, I here, we should measure amount of information expecting from the data set on the parameter theta here. Okay. But well, there is a long derivation before we get this because it's something to do with the log. Is it called log likelihood, right? Something like that. Well, but I just give you the formula here, and then I will tell you the meaning of it later. Okay, and then this is a guy, feature, not a fisherman anyway. Okay, so next, if we consider the uncertainty of parameters theta around the critical value theta c here, it means that you need to expand your log p theta here around theta c, right? With really simple expansion here, and then according, well, this is give you 0 because this is the critical point, and then you end up with this one. And so to look for the error range of the parameter, you demand this quantity to be -1, right? Because it's going to, well, and then because the error parameter can be obtained by, well, varying this value around the maximum, then decrease the factor by half, right? That is a reason. And then even, well, at the end, you will get the variance of this parameter by this reciprocal of the feature information here. Okay. What does it mean here? So this, well, I give you this picture. So it means that the small error range gives you a big value of the feature information and vice versa. So, well, you need to estimate the parameter theta here, right? If your feature information is very high, it means that your estimation is going to be very accurate, right? That is the thing, right here. And then, yeah, it's telling by this picture here. And so in the case that actually if we deal with the set of parameters theta, and then the feature information will turn into this one, which is actually nothing but the feature law metric, which actually I derived before from the Kullback-Leibler divergence, right? Which is actually the same formula. But well, there is the math, some few steps of the math actually coming from this slide to this slide, but it's not that a big issue. But you're going to get this anyway, okay? Okay, so in order to see, well, why is it the metric in this sense? Then I need, well, I'm going to talk a little bit about statistical manifold, a bit, right? So this manifold is nothing but, well, it's a Riemannian manifold, actually, but as parameterized by a probability distribution function somehow. So, well, this is the way that I define the manifold, right? Which is actually, this is a set of prop, and then parameterized by this parameter, which is actually in this, what is the name of this symbol? I don't know. I don't know. Anyway, so, Okay, so well, this is might be a bit abstract. Then let's give you a picture here. So this is space of a parameter, and then this is space of the prop, right? And then you can map this into the prop, and then you map back in, and you can construct a manifold here, that kind of thing. And then this is called, well, statistical manifold, right? And then this is a very simple example. I give you normal distribution, which is actually given by this one. And then with this normal distribution, there are two parameters, mu and sigma here, right? And this mu and sigma will be in the range of real line and the positive real number here, because the variance must be positive, right? Okay, and then it's not difficult to see that actually log of this p going to be this one. And then you compute, well, you compute the Fisher metric, Fisher-Lau metric, you get this Gij, right here, out of it. Because there is only two parameters, then the metric is going to be 2 by 2, right? And then you get this one. And then, once you get this Gij, you can construct the line element, right, in this way. Or you can put, well, you can put in this way. And then with this ds squared, you can compute the distance between 2 points on that manifold, right, by integrating this ds. And then, well, this L is nothing but, well, you can think this is nothing but your Lagrangian here. And then you get this, the Lagrangian this way, right? And then, once you get this Lagrangian, you put into the Euler-Lagrange equation, you will get this equation, right, which it actually gives you the, well, nothing but a geodesic equation. And the solution can be put in this way. And this is center, and the R is radius. And then this is, well, this is known as a Poincare half-plane model. Okay? And if you try to draw a picture, you're going to get this one. It means that, so if this one is a point P, and this one is a point Q, the shortest distance is going to be this curve. Right, here, in this way, in this plane. Okay, that is a thing. And then if you compute further on this, on the board here, like Riemann curvature tensor here, and then you will end up actually, you can show that actually the curvature of this particular manifold is a negative one. All right. Well, you can use it. Well, Chun-Hong can show that later. Anyway, well, this is one of the simplest example of the statistical manifold for this normal distribution here. Okay. Now, the next one is that we call, I don't know, it's called Kamerau inequality here. So we have the unbiased estimator, which is actually the estimator which expectation value is equal to the parameter. And then we have this relation here, right? Okay. And then this big zeta is nothing but the point estimator. And then we consider the derivative, the first derivative of this expectation value with respect to zeta, right? And then you compute it, and then you get this one, and then you get this quantity, but it's actually, is this 0? And then you will get this relation here, and you rewrite it in a very clever way, I would say. You put this relation in this way, and you apply Cauchy-Schwarz inequality, you will get this relation here, which should turn out to be this one. Again, we should actually, we had this relation before when we consider the error range of the parameter that I did, right, when I consider, well, anyway. This is one, this is the bound of the Fisher information. And well, the note is feature information is additive if you have two independent pop, right? It's not difficult to prove that, but well, I just put there. Okay, next, come to the main point. So, action functional. Now, this is the main part of the talk now. After I spent quite a long time to introduce a lot of things. Okay, so there is a work from this guy, Flyden, I would say Lloyd Flyden here. You can look at his book here. In the case of one random variable, the feature information can be put in this way, and then you can parameterize it into, well, you can parameterize it into this way, okay? And again, you can put in this way. It's not difficult at all to see that. And then, if you put in this way, and then you again redefine, you introduce a new parameter that we call Q, which is actually square root P here. You have to keep in mind your P is the probability, but the Q is the square root of the pop. If you're doing this, you're going to get your feature information will be put in this form. The dash is the first derivative, right, with respect to the y. And then, if you look at this carefully, well, according to Flyden, he interpreted this is nothing but the action functional. And then you can say that actually the term inside the integrand is nothing but the Lagrangian right here. And then if you extremize this I, you will get this equation, which is actually the free particle in this way. Okay. So, well, with this connection between feature information and action functional and the Lagrangian in this way, okay. I and Wallace Butgel think about, well, we can extend idea by employing this work with my student at KMUTT. Actually, we studied actually this, well, Lagrangian can be put in this form, which is actually the extended version, or one parameter generalization of this Lagrangian here, the content parameter here. And then if you take the limit on this lambda, you will get back this Lagrangian here. It's not difficult to see that, but the interesting point is that this Lagrangian produce exactly the same, this equation of motion with this one. Okay, and then, and according to this limit, if you take the lambda approach to 0, then you will get the standard Lagrangian back. Okay, this is the point that we think that, oh, okay, we can somehow see the way to generalize the feature information in the case of one random variable. Okay, and then we end up with this one here, new action functional that actually contain parameter lambda here. That actually, this, I would say, well, this is the new one parameter feature information here. And if we expand this lambda I with respect to lambda, and then we get I1, I2, I3, and so we're going to get somehow a hierarchy, right, of the I somehow, which is actually the first one here is the standard feature information, right? And well, and the second one and the third one, well, we don't have really that. We don't know what it should call, but we're going to, well, call it the second feature and the third feature anyway. And yeah, as I mentioned, we have a hierarchy here, and then the first one is nothing but the standard one, which is actually coincide with the limit here. And if we look at the second one and the third one carefully, well, not carefully, closely, we can see that actually the second one you can put in this form. I mean, we can turn this parameter variable Q back into the original variable P here, right? And the third one as well, here, in this way. And we find out actually recalling the two parameter feature information that I just got it from another work, right? And then we can identify that actually our feature information, that the second one, or should be the third one, we should actually somehow you can identify this A and B parameter with the second one, third one, and the fourth one in our context here somehow. Anyway, so next we're going to again we need a bound for our feature information. Then we consider the Q expectation value of this one, which is actually the difference is that the standard expectation value, this is just P, right? For this one is P to the Q here, right? Which is actually this Q is nothing but, well, in this context they call a solid index somehow. And then again we consider the first derivative, and then we get this relation equal to 0, and then where the QQ here is this one, and then the day is this one, right? And then, well, this is not, well, I would say this is, if this, the small q is 1, is going to be 1, right? Because according to the standard condition of the probability. But, well, because we working with the q somehow effective probability, then we have this QQ here. And then, well, by applying, well, we use the Holder inequality, we find that actually J is, well, will be put in this way. We're going to, well, and we going to have more parameter in it. We call alpha and beta must satisfy this equation and must be in this range, okay? And at the end, after we doing this, we end up with this, I would say, extended Camera inequality in this way. And is it not, well, we can retrieve the standard Camera inequality back. If we set Q equal to 1, beta equal to L, and alpha equal to 2, and then we get the standard one back. And then, I mean, standard one is mean for the I1, right? And then for the I2, we set Q equal to 5/4, beta if in this value, and alpha into this value, we get this bound somehow. And then we can keep doing this to the function in the hierarchy, right? Anyway. And then another point is that this new, I should say, is not new feature information. This not additive. It's not additive. I mean, like the second one in the hierarchy, definitely is very clear here. It's not additive. Even this P1 and P2, they are independent. But the first one, I mean, I1 definitely additive, right? And then if you go beyond I2, I3, I4 also, they are not additive as well. Okay, so now we're going to construct two parameter generalized feature information. Now I'm going to rewrite our one parameter feature information in a new form. So I replace lambda by 1 minus lambda here. You see? Okay, and then the standard feature can be obtained by consider this limit by sending lambda to 1. You're going to get the standard feature information for this one parameter situation. So, and then if you look at this, there is an exponential function here, right? So what I did is that I'm going to employ the definition of the Q deformation of the exponential function. And then I get E gamma here. It means that, so I have two parameter feature information already here now. And then by sending this gamma to 1 and then lambda to 1, we get the standard feature information back. Okay? So, well, come to the conclusion. So, in the case of one random variable, we construct one parameter generalized feature information by employing the connection between, well, the least action principle and multiplicative Lagrangian, I would say. And the extended Camara inequality is obtained, right, as I show you. And the one parameter feature, well, this one parameter generalized feature is not additive, as I mentioned. And also the two parameter generalized feature information is also obtained in this way, right? Yeah. The idea can be extended to the case of many random variable, I guess, and that what we are working on now, actually, to go beyond one random variable. And yeah, the last bit is the application of this generalized feature is still a question. We don't know yet what we should do with it. But we just love to do math, then why not? Okay, and we shall need further investigation anyway. Okay, so let me give you this last picture here. For comparison, on this slide we have a diagram for the entropy with no dx here. Sorry, here. But on this side we have this feature information, and we have generalization, one parameter and two parameter here, right? And then somehow we succeed, I would say, in order to generalize feature information in the case of one random variables. Anyway, thank you. That's all for my talk.
Okay, thanks the speakers, and any problem? Okay, so
well, give me only one, please.
Yes, so maybe start by the last one,
Yep.
which is about your last point about the application. So I wonder what is the operational meaning of the new Kramer-Rao bound from the two parameter thing, right? If you go to the slides,
This one?
The maybe.
You mean
yeah, this one. So does it look like you can now your Kramer-Rao bound can bound not only the covariance but higher moments? Is that because you have like the power 4/3 or something like that?
Yes. Yes. Mm-hmm.
Yeah. So, well, like I don't know. Would this be one of the new thing, the application?
I don't know actually. I haven't thought about that.
Yeah, because yeah, I don't know what is the new. Okay, so the original Fisher give you Riemannian metric, right?
Yes.
So does this one also give you a Riemannian metric on the simplex?
You mean for the Riemannian metric is you mean what you mean the example that I gave, right?
Yeah, like
this one, or
so even for the simplex, right? Maybe could you go to the
right, okay.
simplex? Oh yeah, this one. Yeah, so the original the Fisher metric is just so you have a flat simplex, but when you use the Fisher metric is popped up to be the round metric, right? So basically it's like the status of space is round. So if you use your new Fisher information, does it give like an actual different metric on this simplex?
Yeah. Again, I don't know. Yeah, we have. Yeah, I don't know. We haven't thought about that. Yeah. But yeah, I am going to think about that. Yeah. Thank you anyway.
Oh no, thank you. And maybe the last question.
Okay.
So when you have equation of motion, so when you say you think about the Fisher information as the integral of some Lagrangian density, right?
Yes.
Yeah, and then you add some parameter in, and then you say, oh, it gives you the same equation of motion.
Yes.
Yeah. So does that equation of motion has any interpretation? Like, does it have any meaning in the sense of statistics?
In the sense of statistics.
Statistics.
Right? Well, yeah, that is. That I don't actually. Again, I don't know because well, there is a lot of things that I don't know. But the thing is that the argument of the Flyden is that so he believed that actually from this kind of connection for any physical system that we have somehow can be connect with this kind of extremizing feature information. That's what he tried to argue. But I really don't know that you mean this equation going to give you somehow of statistical meaning, right?
Yeah, so I mean, for example, like in this case, you say you have the same equation of motion, but if you get a different equation of motion, is that a problem?
Well, but in this situation, we get the same equation of motion.
Yeah.
That
Yeah. Like, is it a good thing? Is it necessary to?
Well, the motivation of doing this, I mean, by extend this one to this one, is somehow related to the what the problem is called inverse problem of calculus of variation. So normally in a standard context, when you write the Lagrangian, right, you know how to write the Lagrangian, but you never solve it, right? Because if suppose that you have Euler-Lagrange equation, and you could think that actually your Lagrangian is a solution of that set of Euler-Lagrange equation. The question is that, how many solutions or how many different of Lagrangian that's going to satisfy that Euler-Lagrange equation? That's what we did, and then we came up with this Lagrangian. But that still give us the same equation of motion. That's our constraint.
I see. So like in physics, it's clear that whatever physics that you have, you need to have the same equation of motion. But in this case, it works the opposite way. Really, that is the motivational principle to find a new, like, the generalization way. I think that's what I got from your answer.
Again, can you say again? I cannot hear you clearly.
That is so in this case, so as sort of like an opposite direction from physics, from what you say, is more like now wanting to have the same, how do I say it? Wanting to find a way to modify the Lagrangian to give the same equation of motion is now sort of like a motivational principle.
Oh, right, okay. I guess I kind of get your point.
It's like how it's a guiding of how I should generalize the Fisher information.
But let me put another point. So actually, you can expand this Lagrangian with respect to parameter lambda here, and then you will get the hierarchy of the Lagrangian here. like the L1 is the standard one, the L2, L3, L4, right? Which is all of them give you exactly the same equation of motion or give you the same physics. But the problem here with doing this with feature information, we don't know what is, well, we know what is this for the first term because this is the standard feature, right? But we don't really know what is I2 and I3 in terms of the meaning of it or application of it.
I see.
That is the issue that we have. And then, well, I and my student discussed actually at the early stage of this work, we believe that actually this one and this one might somehow related to what the tail of the distribution somehow that we call kurtosis somehow, right? Is that somehow? But well, we don't fully understand that yet. Yeah.
Okay. Yeah, thanks a lot. Yeah, I think that make this part clearer to me.
Okay,
Thanks.
Thank you. Thank you for your question. I'm going to discuss with your first two questions again. Anyway.
Okay, so any other questions?
No.
No? Okay. And from the website?
No. Okay.
Okay, so if you have some further questions, you can personally discuss with Sikarin.
Yeah, sure.
Yeah, and let's thank our speakers again for the wonderful talk. Yes.
Okay, thank you very much.